Okay, today we're going to tackle one of the most powerful technologies out there, neural networks. But we're not just going to talk about them. Oh no, we are going to build a simple one right here from the ground up to really see how these things actually, well, think. Let's dive in. So it all kicks off with a question that honestly feels a little bit like magic. How does a computer know this is a cat? I mean, you point your phone at something fluffy and bam, it knows. How? It's not sorcery, I promise. It's actually a really brilliant process, and we're going to break it down piece by piece. So, how did we even get to this point? Well, this whole AI revolution wasn't some single eureka moment. Nope. It was more like a perfect storm, a combination of three key ingredients all coming together at just the right time. First, you've got just massive amounts of data. I'm talking millions upon millions of cat pictures online. Second, we finally got the raw computing power to chew through all that data thanks to GPUs. And third, the secret sauce, smarter algorithms that could actually learn from all of it. Okay, to get our heads around this whole thing, we have to start small. And I mean really small. We need to look at the most basic building block of it all, a single digital neuron. Just for a second, forget all the complex code. Just picture it as one tiny little decision maker, like a single voter. Now, the super technical term for this little voter is logistic regression, but don't let that fancy name scare you off. Seriously, at its core, all it does is look at the evidence from an image and make one super simple decision, a thumbs up or a thumbs down. Is this a cat? Yes or no? That's it. So how does that single vote actually happen? It's a pretty straightforward three-step process. First, the neuron gets fed the image data. Then it starts weighing the evidence, looking for catness. Things like pointy ears, whiskers, that kind of stuff. And finally, it makes the call. It casts its one and only vote. Cat or not cat. But a single voter can only answer a simple yes or no question. And let's be real, the world is way more complex than that. So to tackle the bigger problems, we can't just rely on one lonely neuron. We've got to build a team. And that brings us to the next logical question, right? What happens when the answer isn't just cat or not a cat? What if we need to decide between a cat, a dog, and a bird? All of a sudden, our simple little yes-no voter, well, it's just not going to cut it anymore. And this is where we get the solution. It turns out there are two main ways our new team of neurons can vote. So on the one hand, you have what's called the sigmoid approach. Think of this as independent choices. Each neuron gets its own vote. Is it a cat? Yes. Is it a dog? Yes. It's totally possible for both to be true at once. But then, on the other hand, you have softmax. And this is a totally different game. Here, the team is forced to make one single choice. They have to spread 100% of their confidence across all the options. So only one can win. The final answer becomes something like, okay, team, we're 70% sure it's a cat, 20% a dog, and only 10% a bird. Okay, so the network makes a guess, but how does it know if that guess was any good? I mean, how does it learn? Well, that's where something called the loss function comes in. The easiest way to think about it is like a report card. It literally gives the network a score that measures how wrong it was. And the whole point of training is just to get that wrongness score as low as you possibly can. All right, so we've got our inputs, the picture, and our outputs, the guess. But now we get to the part that actually makes a neural network deep. This right here is where the real magic happens. We're talking about the hidden layers. They're called hidden for a pretty simple reason. We don't directly program what they do. They actually learn all on their own. They build up this really sophisticated understanding of the world, step by step, starting with super simple ideas and building up to much more complex ones. So let's imagine that first hidden layer. Think of it like a team of super focused specialists. Each little neuron has just one very simple job. One is looking for horizontal lines. Another is looking for a specific curve. A third is just looking for a patch of orange fur. That's it. They don't see the whole cat. Not yet. They just see these tiny, basic pieces. Okay, now we get to the second layer. Its job is to take all the simple stuff that the first layer found and start combining it. So it starts putting those simple edges and colors together into more recognizable shapes. A neuron in this layer might learn to spot two triangles on top of a circle and think, hey, that looks like ears. Another one might see a bunch of straight lines close together and say, I think those are whiskers. And finally, we get to the output layer. This is the big boss. It takes all of these collections of parts, the ears from one neuron, the whiskers from another, the eyes, and it puts the whole puzzle together. It sees all the components and then, probably using that softmax function we talked about, it confidently declares a winner. Yep, that's a cat. So the network can make a guess. That's great, but that's not the amazing part. The amazing part is, how does it actually learn? How does it get smarter every time it makes a mistake? Well, the answer is in this really simple but incredibly powerful feedback loop. The whole learning process really just boils down to a simple two-step dance. First, all the information flows forward through the network so it can make a guess. That's called forward propagation. Then, depending on how wrong that guess was, the corrections start flowing backward through the network. And that correction phase, that's called backpropagation. And let me tell you, this is the secret sauce. This is pretty much the engine that drives almost all of modern AI. So after a wrong guess, the network literally works backward from the mistake and tells every single neuron along the way, hey, you need to adjust your vote just a tiny bit so we're more accurate next time. It's exactly like a coach giving notes to the entire team after every single play. Now, you're probably thinking, this whole guess and correct loop sounds like it would take forever, right? One picture at a time. And you'd be right, it would. Except for one amazing trick called vectorization. This is the secret to why modern AI is so fast. Instead of feeding the network one single cat picture, GPUs can process thousands of them all at once in a giant batch. This lets that whole learning loop run in parallel, and it's what makes the network get smarter incredibly fast. And that's basically it. We've gone from one tiny, simple voter all the way to a deep network that can genuinely learn on its own. We've kind of built the blueprint for a simple digital brain. Which, of course, leaves us with one last really big question. Now that we know how to build it, what are the next problems we should teach it to solve?